Hello, everyone, and welcome to today's webinar. My name is Patrick Hawkins. I'm a design engineer in the Thorlabs Advanced Photonics department and will be moderating today's talk. Today's presentation is Optical Fiber 101, Understanding Single-Mode Fiber, and will be given by Dave Gardner. Dave has been with Thorlabs for over 10 years and is currently working as a senior process engineer. Within his role, Dave leads the development and production of our fluoride fiber, while also supporting the characterization, testing, and R&D for our silica and fluoride manufacturing teams. Dave also plays a major role in the development of new fiber products and processes. This webinar is part one of a two-part webinar series on single-mode fiber. In this section, we're going to help demystify single-mode fiber by looking at it from a theoretical perspective. We will take a look at what single-mode guidance really means and how to think about important properties like cutoff wavelength, attenuation, bend loss, and more. In part two, we'll be taking a look at the practical aspects of using single-mode fiber, like how to achieve efficient coupling of light into small core fiber, amongst other things. Everyone who is registered for part one will be automatically registered for part two and will receive a confirmation at the end of this section. I've worked in the product development team at Thorlabs for nearly 10 years, during which time I've worked with Dave quite a bit on R&D products, new metrology equipment and processes, and introducing new fibers and accessories manufactured in our Advanced Photonics division. We are accepting questions throughout the entire event. To submit questions, just click the Q&A button in the top right of the screen, and Dave will address those at the end of the talk. Okay, I'll turn it over to Dave now for part one of single-mode optical fiber.
Thanks, Pat. Thanks for the introduction, and thanks to everyone who joined us today for the first of our talks on single-mode fiber. We'll jump right into it. Here's a little outline of what we're going to talk about today. Today's talk is single-mode fiber in theory, but we're really going to talk about single-mode fiber from a conceptual standpoint, from a practical standpoint, more so than going over, all the math, for instance, and looking at it in that way. The goal here is for this to be a high-level overview of, how single-mode fiber works, so that, for instance, if you're working with single-mode fiber in a laser lab or other environment like that, you have a good conceptual understanding of what's really going on inside the fiber. So we'll start with some basics on optical fiber, talk about what does single mode really mean. We'll go through some notable behaviors of single mode fiber and how they differ from other fiber types. Well, with a special focus on the attenuation of single mode fibers, I think that really sheds a lot of light onto how the fiber behaves. And then we'll conclude with a short section on designing single mode fibers and touch on a few things about single mode fibers in the real world versus the theory. So this first slide is we showed this in our previous fiber talks. It's kind of a review, but of course, optical fibers function by total internal reflection, where you have a medium with a higher index and a lower index. And if you have a light ray that's incident on that interface between the two mediums at a shallow enough angle, below what we call the critical angle, we get what's called total internal reflection, which is 100% reflection. In an optical fiber, rather than, for instance, water and air or glass and air where you have index of 1.5 and index of 1, we use two different types of glasses with a very slight index difference, less than 1%, sometimes even less than 0.5% for single mode fibers. And those two glasses are arranged in a structure where the central portion is called the core, and then it's wrapped with a section called the cladding around it. And a light ray can experience total internal reflection on that core to clad interface and be guided along the fiber. So an optical fiber, really how it's functioning, what we could call this is a cylindrical waveguide or radially symmetric waveguide. Now talking about types of optical fiber, what I just described is called a step index fiber. What that means is we have a cladding of one homogeneous index and then a core of another index, and then there's a step change in the index between the core and the cladding. For this talk, we're really going to focus on step index fibers and really the most simple step index fiber design. That can be shown in a diagram like this. We call these index profiles. And what we're showing here is the x-axis is traversing along the fiber. So the middle would be the center of the core, and then to the right and to the left is going through the core and then out into the cladding. And then the y-axis is index of refraction. So you can see here, this is kind of the classic fiber design where we have a core region with a certain index surrounded by a cladding with a lower index, and that's radially symmetric. This index difference is typically pretty small. For single mode fibers, less than 0.5%. And so these fibers, I said it's as a cylindrical waveguide. Fibers are technically speaking a weakly guiding waveguide. There are other types of fiber, which we're not really going to cover in this talk, but for instance, graded index fiber, where the index of the core is a parabolic shape, or some more complicated fiber designs, like this one we see here, where there's a so-called trench lower index region right around the core. Those can be engineered for different advanced applications. So to talk about single mode fiber, the first thing to talk about is modes. So the ray theory, or what we kind of showed in the first slide, the light pipe theory of a fiber, which is what you would get in an intro to physics class, for instance, we'd think about the light propagating through the fiber like this, where there's going to be a light ray that's going to experience total internal reflection at the core cloud interface, and it's going to bounce along. And you could have multiple path lengths, a very shallow angle, a steeper angle, an angle that's almost at the critical angle, can all be guided through the fiber. The light can take multiple paths. So that's the ray optics interpretation. If we think about light as a wave, the way we would describe this is modes. Simplifying a little bit, but the modes are roughly analogous to the different paths that the light could take through the fiber in the ray optics interpretation. And so if you have a light source that's coupling light into the fiber, and you have the light traveling couple different paths, the way we would talk about that is there's going to be light in the fiber is going to be a power distribution between different modes. So there'll be an intensity distribution, some light in one mode, some light in the other mode, etc. The modes, what are they? So for fibers, we can describe the modes as linear polarization modes, or LP modes. We can use these modes because of the fiber's radial symmetry that I mentioned, and also because it's a weakly guiding waveguide. And these are a bit simpler to think about than, for instance, in a rectangular waveguide where we have to think about TM and TE modes. Because the fiber is cylindrical, we don't need to do that. So these LP modes, basically they correspond to solutions of the wave equation for complex electric field profiles in cylindrical coordinates. We're not going to go into that math, but suffice to say they have two indices. The first number being kind of an azimuth index, which is just increasing 0, 1, 2. And then the second index is basically how many solutions you have for each of the first indices. So you can see LP 0, 1, LP 1, 1, LP 1, 2, et cetera, et cetera. It's worth noting that the modes where the first index is greater than 1, where we have these lobes, really what those are two modes orthogonally to each other. So for instance, for this one, we could have left, right lobes, or top and bottom. And then any real mode is going to be a superposition of those two. But we're going to disregard that and treat them as one mode for this talk. We're also going to disregard polarization states. Even this LP01 mode, it's a linearly polarized mode. So in reality, you could think of it as two orthogonal polarization states, and any real world scenario would be a superposition of those two states. Again, we're going to disregard that for this talk and refer to it as one mode. So with those modes in mind, we can talk about not a single mode fiber, but a multimode fiber. Really, a multimode fiber, the definition is any fiber that can support multiple modes. We're showing you a few modes in this chart here. A typical multimode fiber actually supports thousands of modes, though, and that thousands of modes is really what that ray optics interpretation of the fiber, that's what that's an approximation of. So that's a multimode fiber. In contrast, next we're going to talk about what is a single mode fiber. So I think the best way I can think of to explain a single mode fiber is a quick theoretical thought experiment where we can think about a multimode fiber, a step index multimode fiber, with a relatively small core. So instead of the 50 or 100 or 62.5 micron core of a typical multimode fiber, let's call it on the order of 10 microns. And we're going to start with UV light, short wavelength light, into that core. And we're going to gradually increase that wavelength of light that's being guided through the core. We're going to couple in a single wavelength at a time at longer and longer wavelengths. So if you think about how the light, quote unquote, sees that core, or sees this waveguide structure, as the wavelength of light gets longer, it sees the core basically as being smaller. So you can fit less waves, so to speak, in the core. Of course, this core, as it gets small and we're on the order of a few wavelengths, we can't really think of that ray optics interpretation anymore. It's purely the modes and the wave optics interpretation. So yeah, as the wavelength grows longer, the core effectively gets smaller. Now, those modes that I showed you, we can think of, flip back real quick, from the bottom to the top or from the left to the right, low order modes to high order modes. Those higher order modes, as we increase the wavelength or effectively shrink the core, one by one, those modes can no longer be guided by the core. They kind of no longer fit. And so what happens is if we exceed a certain wavelength for each of those modes, now that mode is too large to be guided within the fiber. The fiber no longer functions as a waveguide and the mode leaks out of the fiber. So one by one, as we increase the wavelength, these modes no longer fit. Eventually, we only have two modes left. The second mode, LP11, eventually falls out of the fiber, is no longer guided as the wavelength gets long. And then as the wavelength continues to grow, eventually that first mode, LP01, no longer fits in the fiber. It no longer can be guided. At that point, the fiber ceases to guide any light. It's no longer a waveguide in any sense. And from that thought, we can define a single mode fiber. So a single mode fiber is a fiber with a construction such that there's a wavelength range between that second mode and first mode cutoff, where it can guide only that LP01 mode, which we call the fundamental mode. So single mode fiber is a fiber that only guides LP01 within a certain wavelength range. And we would refer to that wavelength range between that second mode cutoff and the first mode cutoff as the single mode operating wavelength range. So this diagram here hopefully illustrates that. What we're looking at here is the x-axis is wavelength. So we're starting with short wavelengths and the wavelength gets longer as we go to the right. So we have many higher order modes cutting off. As we increase the wavelength, eventually we get to a region where that second mode's cut off. Below that, we have multiple modes guided. So we have multi-mode operation. At a wavelength longer than that second mode cutoff and before the first mode cutoff, that's where the fiber operates in the single mode regime. And then beyond that, after that first mode is cut off, the fiber no longer guides light at those long wavelengths. So that really is the crux of what a single mode fiber is it's only guiding the LP01 mode. The next section of the talk, what we're going to do is we're going to talk about that fundamental mode. If we only have that fundamental mode propagating through the fiber, there are some unique properties of that fundamental mode that we can take advantage of. If it's the only mode that can be guided through the core, yeah, there's some special properties that we can take advantage of, and that's what we'll go through on the next section. So the first thing to talk about is how does that fundamental mode propagate through the fiber? So again, the classic ray optics interpretation of the multimode fiber is the light, flip back a few slides, bounces off this core cloud interface. In a single mode fiber, if we were to cross-section the fiber and look at the light going through, we'd see something like this. So you can see our core and then our cladding, and that fundamental mode is actually a bit larger than the core. It extends into the cladding some, and this again is due to the wave nature of light, and it's the ray optics interpretation really breaks down for single mode fibers. What we're showing down here is kind of along this axis in the fiber. The blue line is the index profile, which we showed on a previous slide. So you can see cladding, core, cladding. And then this black line is the index profile, which extends out into the cladding. Not only does it extend into cladding, but this intensity profile is almost perfectly Gaussian. So almost matches a Gaussian beam, or a beam described with a Gaussian function. Not quite, but close enough that we can really treat it as a Gaussian beam for all effective real-world purposes. It becomes helpful to define, the region where this light propagates, which is larger than the core. We call that the mode field diameter, and what that is the 1/e² diameter of intensity of this so-called Gaussian beam, or this fundamental mode. And that mode field diameter ends up being what we can talk about as the effective core size of the fiber when we're doing things like couple into the fiber. Like I said, that mode field diameter, or that beam, is larger than the core, and believe it or not, around 45% of the power, of the optical power, propagates in the cladding rather than the core. Even though it's most intense in the center of the core, there's a lot of surface area out here. So that's how the fundamental mode propagates through the fiber. The next thing we're going to look at is what happens to that fundamental mode if it exits the fiber, if we output the light into free space. And here's where we're going to really start comparing the single mode attributes to a multimode fiber. So single mode output beam, as we see here on this image, we basically coupled light into a fiber and then had a cleaved output face and shined that far field pattern onto a screen to take this image. So we see that output pattern is also nearly perfectly Gaussian, or an m² value close to 1. And that's in contrast with the multimode fiber's output pattern, which is, for lack of a better term, messy. In the multimode fiber, you have multiple modes, of course, and let's say you launch coherent light, like a laser, into the fiber. All those different modes are going to, within that large core area, constructively and destructively interfere with each other. So we get this characteristic speckle pattern of regions of constructive and destructive interference. Contrast that with the single mode output profile, where we don't see any of those effects. And the single mode fiber, like I said, the output pattern is nearly perfectly Gaussian, and that actually remains the case regardless of the launch conditions. So if you launch a beam into the fiber that's not Gaussian, you do get a Gaussian beam out the other end, which can be a very useful property for things like a mode filter. The cost of that is, if you launch a non-Gaussian beam in, you get the Gaussian beam out, but that's at the expense of coupling efficiency. So what we don't see is perfect, 100% or near 100% coupling efficiency, because if you think of that non-Gaussian input beam being coupled into the fiber, really it's a superposition of two states, the Gaussian portion and the non-Gaussian portion, and only the Gaussian portion can be coupled into the fiber. So the rest would not be, but what comes out the other end of the fiber is this beautiful Gaussian output pattern. So building off of that, in addition to this nice output pattern, single mode fiber also behaves differently than multimode fiber as it's bent. So we call this bend insensitivity. In a multimode fiber, if you bend the fiber while light's propagating through, what we see is bending the fiber. Of course, now we don't have a straight line, a straight waveguide anymore. So we're going to have some of the optical power, that power distribution between modes is going to change. So you're going to send some of the optical power typically toward the higher order modes as you bend the fiber. Because we have different modes now propagating through the fiber, that means if you bend the fiber, bent versus straight, you're going to get a different output pattern. It's going to change some because we're changing the distribution of modes. In addition, like I said, you're going to transfer power to the higher order modes, which tend to be lossy, more susceptible to attenuation. So if you bend the fiber, you're going to see increased attenuation because you've sent some of the optical power to those high order modes. In contrast, in the single mode fiber, the fundamental mode's propagation, it's relatively unaffected by bending the fiber. Again, the fiber only guides one mode. You can't transfer power to higher order modes. So we see, first of all, that means no change in the output pattern as we bend the single mode fiber. And we also see that at a given NA, we see that or a given, light guiding strength, let's call it, the single mode fiber is going to be less sensitive to bending or bend-induced attenuation compared to the multimode fiber, in addition to retaining that constant output profile. So to illustrate this, we took some movies in the lab here at Thorlabs. So this experiment, what we're doing is we just have a multimode fiber first, and then we'll show the single mode version. It's in a patch cable. And what we're doing is we're going to bend the fiber back and forth right behind the connector. So introducing a bend in the fiber. And we're viewing the output pattern on the screen, and we're going to see how the output pattern changes as we bend the fiber. So first, the multimode example. As we bend the fiber, you can see this speckled output profile kind of dances around and changes, the intensity at each location is wildly changing. I'll play that one more time since it's a little fast. And you can see the speckles all moving around. That's as we're moving power between the different modes as we bend the fiber back here. So now in contrast, we're going to repeat that experiment with the single mode fiber. As you can see, we bend the fiber and we don't really see any change to the output profile of the fiber. And again, I'll play this one more time. Tricky thing to photograph, but hopefully that illustrates it pretty well. So all of these desirable characteristics of a single mode fiber do come at a cost. So that's one thing to note is, again, like we talked about originally, to make the fiber single mode, we need to make the core of the fiber relatively small. So we're showing an example here. These are cross section of a fiber where we've cleaved the fiber and then imaged it under a microscope in our metrology lab here at Thorlabs. And we're comparing on the same scale a single mode to a pretty small core multimode fiber. And you can see the single mode fiber's core is much smaller. Again, that's what we have to do so that we only guide the fundamental mode. And that means that effectively getting light into the fiber with good coupling efficiency is tricky. You need a very high degree of mechanical positioning of the coupling components, positioning the fiber tip and the beam and the lens and things like that. In addition, if you have mechanical splices or other interconnections between two fibers, it's easy to have high loss if the parts aren't well toleranced. 9-micron core, you can imagine, you can't have many microns of repeatability error or offset between two fibers to get good coupling efficiency. In contrast with the multimode fiber, much easier to work with because we have a large core. Like I said, even this 50-micron core multimode is relatively small as they go. In addition, that input beam has to have a m² value close to 1 or a very nice Gaussian beam if we're going to want to have good coupling efficiency into that fundamental mode. So not deal breakers, but things to keep in mind. We'll talk a lot more about this in part 2 of the webinar, where we're talking about hands-on using single mode fiber. The next property has to do with data transmission or telecom uses for fibers. Not really the focus of this talk, we're just going to scratch the surface, but I thought it was bringing up. Single mode fibers are used extensively in the world for data transmission. A lot of the properties we've discussed are very advantageous for things like long haul telecom across continents or under the ocean from one continent to another. So one aspect of that is a lack of what's called intermodal dispersion. And that's because in the single mode fiber, the light can only travel along in one mode. It really only has one path to travel through the fiber. We don't have different modes with different effective path lengths like you do in a multimode fiber. I think this is pretty easy to illustrate with the ray optics interpretation. So let's say you're sending pulses of light through the fiber as you would in a data transmission application. If you send 2 pulses into the multimode fiber, each one of them tends to get broadened in time, even if they're at a single wavelength. So what you get at the other end might look something like this, where now, okay, it's getting it pretty hard to differentiate those 2 pulses on the detector side. Whereas on a single mode fiber, the path length is the same. There's only one path length. So we don't see any of this intermodal dispersion where different modes show up at the other end of the fiber at a slightly different time. As I said, we are just scratching the surface on data transmission and just general types of dispersion. There's something called chromatic dispersion, for instance, where different wavelengths propagate at a little bit different velocity through the fiber. So we will see some broadening, but very advantageous using the single mode fiber to send data through. Last property we'll talk about is attenuation. So attenuation basically means if we put in some certain amount of light into one end of the fiber, how much do we get out the other end, or how much is lost in between? So single mode fibers can typically have much lower attenuation than multimode fibers. It's basically because one of the factors is light is only guided in that LP01 fundamental mode. We can't have that effect I mentioned where you're going to transfer power into those lossy higher order modes. Those modes are lossy in general and extra lossy when the fiber is bent. So that, amongst a lot of other reasons, is why single mode fibers consistently these days set the world record for attenuation. What we're showing here, this is obviously a very old diagram from the early days of optical fiber design. You can see single mode fibers overtake the multimode fibers for the world record in attenuation. So speaking of attenuation, that's a good segue into the next part of the talk, where we're going to examine the attenuation of a single mode fiber as a function of wavelength in more detail, because I think that really shows a lot of these behaviors I've been talking about, how the modes propagate through the fiber. So the first thing that we're going to look at is what we call bend-induced attenuation. So what that means is, let's say you have a straight piece of fiber that you have light propagating through, and then you take that fiber and you bend it in the middle. You put a bend, one loop, let's say, of a certain radius. What we're going to examine is how much attenuation does that loop cause in the fiber? How much less light do we get out the other end when we have the loop compared to not having the loop? So this is a real world test that we've done, again, in our metrology lab here at Thorlabs, and we're going to look at real test data. But first, here's just a quick schematic of the test. So we have a broadband light source coupled into the fiber, and you can use a pretty short piece. We used about 2 meters. And then at the other end, we have a detector. And we used an optical spectrum analyzer. That way we can look at the optical power at each wavelength across a broad range of wavelengths. So first, we take a measurement with the fiber straight, and we get a curve of optical power versus wavelength. Then we take the fiber and we put one loop into it, and we use a radius of about 25 millimeters for this example test. And then again, take a scan with the OSA, look at the power versus wavelength. And then we can compare those powers at each wavelength, bent versus unbent, and we can get a graph of bend-induced attenuation as a function of wavelength. So when you do this test, you get something that looks like this. What we measured here is Corning SMF28 Ultra fiber. SMF28 by Corning is kind of one of the de facto standard for telecom or long-haul telecom in the world. Really a classic single mode fiber design, a very common fiber. So I thought that was a good example to show for this talk. So this is what we measured in our lab here at Thorlabs. And what we're seeing here is these peaks at certain wavelengths. So what we can think about here is going back to my original explanation of single mode fiber. As we increase the wavelength, certain modes, at certain wavelengths, each mode is going to no longer be guided in the fiber. This measurement really is mode blind. It can't, it's not going to say, okay, you have this much power in the first mode, this much power in the second mode. At the end of the day, that OSA just uses a photodiode. And so what we see is the measurement is just the average of all guided modes at a given wavelength. When we bend the fiber, of course, the fiber wants to send some of the optical power maybe into those higher order modes if there are 2 modes, and those higher order modes become extra lossy when the fiber is bent, because that mode is, if you get close to where that mode doesn't fit in the fiber, that that mode is very weakly guided by the core. So bending the fiber can cause the mode to experience very high attenuation. So that's what we're seeing here. Let's talk about this peak around 800 nanometers first. So down here on this kind of baseline level, we have a few modes propagating in the fiber. And then as we increase the wavelength, we start to see the fiber attenuation, the bend-induced attenuation go up. And that's because one of those modes is now getting pretty close to where the fiber can't guide it. It's getting very sensitive to bend-induced losses. And so we see the attenuation increase. As we continue to go to the right on the curve or increase the wavelength, now that we passed the peak, that mode is, a lot of it is being lost in that 2 meters of fiber. It's not making it to the detector. So that peak, we start to see the attenuation, the bend-induced attenuation go back down as that mode makes up less of the total power in the fiber. And then eventually we return to our baseline level where that mode is now gone. It's no longer guided in the fiber. So again, we're comparing over here the bent fiber to the straight fiber, but it's only the other mode, that mode that fell out is no longer included. So we see just a kind of low-level bend-induced loss where all the modes are attenuated a little by bending the fiber. So this behavior where the mode, we've described it a few times in the talk, where the mode experiences high attenuation and then disappears, that's called mode cutoff. And we would call the wavelength where that mode is now no longer in the fiber, guided in the fiber at all, we call that a mode cutoff wavelength. And as you can see, we have 3 different peaks. That's 3 different modes being cut off. Of course, as we go to longer wavelengths, we have less total modes in the fiber. So each individual mode makes up a larger portion of the total light being guided through the fiber. And that's why you see each peak get taller. This mode is maybe 1 out of 5 modes. So it's, I'm simplifying here, but maybe 1/5 of the optical power. So it's a small peak. Maybe now we have 1/4 of the optical power. Now we have 1/3. So we see these peaks get larger and larger. Interestingly enough, one last nuance to point out in this curve, as I said, you have some sort of low-level baseline bend-induced attenuation where all the modes are attenuated some at all wavelengths as you bend the fiber. What about over here? This goes to basically 0. And that's the behavior we're going to investigate on the next slide. The next slide deals with what's called the cutoff wavelength. The cutoff wavelength, or the cutoff wavelength peak, that is where the second mode no longer is guided by the fiber. And so that's where we transition into actual single mode operation of the fiber. So again, same behavior as before. We have multimode operation over here, 2 modes to be exact, LP01 and LP11, these guys right here. As we move to a longer wavelength, that LP11 mode, okay, now it's starting to be a little too big for the core. It's getting lossy, it's getting bend sensitive. As we bend the fiber, we see a lot of attenuation. Now, as we move to this side of the curve, LP11, there's not much of it making it through the fiber, bent or straight. So it's, not much left. And then over here, now we have only the LP01 mode able to be guided through the fiber core. And look at that, the bend-induced attenuation is, okay, there's noise in the curve, but it's basically 0. And that's because that LP01 mode, as we discussed earlier, is really not sensitive to bending. You don't see a lot of bend-induced attenuation. And that's the only mode that's being guided in the fiber. So that's the only mode being measured by our measurement here. The cutoff wavelength is described as where we have 0.1 dBs of loss from that second mode and beyond. So that's really where we think about the single mode fiber only guiding one mode and really being true single mode operation. So next slide, we're going to basically take this curve and look further to the long wavelengths and see what happens, which looks like this. So again, same LP11 cutoff wavelength peak and our cutoff wavelength. Now we have this single mode operation where the fiber has basically no bend-induced attenuation. And now we see another peak start to form over here. So what's happening here is now as we increase the wavelength further, that LP01 mode no longer, it's becoming more weakly guided in the core. It's more sensitive to bends So if we put a bend in the fiber and look at how much attenuation it causes, we see an increase in attenuation. And really what this is the left side of the peak, just like here. We just can't measure the rest because this is the last mode. So maybe there would be a big peak here if you had some sort of magical, mode -1. But the fiber doesn't guide light, so we can't measure that. So what this is called, it really is the start of another cutoff wavelength peak for that LP01 fundamental mode. We call it the bend edge. And that's really where the fiber stops guiding light. So if you want to talk about how is the fiber specified for single mode operation, it goes from the cutoff wavelength out to where you start to see bend-induced attenuation, the beginning of the bend edge, at a certain long-term bend radius. 25 millimeter radius for our test here. Fibers could be specified at a different radius. So this is what we're illustrating here really is multimode operation, bend-induced peak from that second mode, single mode operation that's bend insensitive, and then now bend-induced attenuation of the fundamental mode. And fun fact, fiber manufacturers tend to be pretty conservative when they're speccing the wavelength range for these fibers. They really don't want you to see bend-induced attenuation. So SMF28, I don't remember the number, but it's definitely not specified to work past 2 microns. As you can see, though, it does guide light. There is some bend-induced attenuation, but you can actually use this fiber for certain applications at 2 microns or even beyond if you're very careful to not have any sharp radius bends in the fiber and you accept some attenuation. So talking about the radius of the loop, that brings us to our next graph, another thing we measured. What we did is basically this same measurement, but we measured at a variety of loop sizes. And that gives a curve like this. So our original curve in the dark blue is still here, the 25 millimeter radius loop. And then as you can see, we did 20 millimeters, 15, 10, and 5. There's a couple notable things that are going on here. So let's first look at the higher order modes cutoff and the second mode cutoff peaks. As you see, as we make the loop smaller, those modes start to get lossy sooner at shorter wavelengths. But that cutoff, that fundamental mode cutoff, always occurs at the same wavelength. So they get lossy in bending at shorter wavelengths. But when you want to talk about, okay, that mode is gone, it's no longer possible to guide that in the fiber. That always occurs at the same wavelength, no matter what you make the loop size. In addition, looking at the bend insensitive single mode range, that 25 millimeter loop, we get a really wide wavelength range where it's bend insensitive. And it pretty quickly moves in as we make the radius of the loop shorter. Once we get to 5 millimeters, if we're bending the fiber so tightly, we only have a very small notch where it's going to guide the single mode light with almost no bend sensitivity. To be fair, a 5 millimeter radius loop is like wrapping the fiber on a pen, so you wouldn't do that in a real application. But it just goes to illustrate how the fiber behaves, losing light as it's bent with different radius bends. As I said before, you can use the fiber further into the IR if you minimize the radius of the loops. There is another factor called microbending that we'll talk about later, where we effectively have the fiber, even if it's straight, it does behave like it's bent a little bit. We'll talk about that later. So that's a limiting factor as well. The next thing I want to show, in the last part of our attenuation deep dive, is what we would just call spectral attenuation. So up till now, I've been showing you how much attenuation is caused, all else held equal, by putting a loop into the fiber. Next, what we're going to talk about is if we couple a certain amount of light into one end of the fiber, and the fiber goes through a long spool of fiber, let's say many kilometers long, how much light comes out the other end? How much light is lost along that length of fiber? And we can look at that as a function of wavelength. So for this test, again, we use a broadband light source and an optical spectrum analyzer. And what we're going to do is we're going to couple light into a long spool of fiber and look at how much light comes out the other end at a function of wavelength. And then without changing this launch condition, we're going to physically cut the fiber right here, a couple meters back from the launch, and then hook up the OSA to this P0 point and do the same scan, measure power versus wavelength there. we can compare P1 and P0, and that basically can tell us how much light is lost between those 2 points. This is called a cutback test, and it's the standard way we would measure attenuation for a spool. We can divide that number by the length of the spool, and we can actually get attenuation per meter, or average attenuation per meter, usually expressed in dBs per kilometer. So if we do this test on our SMF28 fiber, we get a curve that looks like this, and this curve can tell us a lot. As I said, even when the fiber is, not nominally bent in a small loop, it's still wrapped around a spool, and it still does have microbending. So it kind of does behave as if there are some bends, and that's why we still see these mode cutoff peaks. This is the LP11 mode cutoff. Beyond that, we see very low attenuation. So fiber is not very bend sensitive. It doesn't really have much attenuation otherwise to speak of, and we get this region of low attenuation. On the right-hand side, we do see characteristic increase of the attenuation. And if you recall, that bend-induced attenuation curve was still pretty close to 0 all the way out at 2000 nanometers. This one's is further in. And why is that? The reason is we have that bend edge, that behavior where the fundamental mode becomes lossy with bending. But we also have a second factor, which is material absorption. When the light goes through a fiber, it's passing through glass along that whole multi-kilometer run. And silica glass, which we normally make optical fiber out of, starts to absorb light at a low level when you get around close to 2 microns or 2000 nanometers. That's due to multiphonon absorption, as we call it, which is basically the molecular lattice is absorbing those photons into vibrational energy. So the lattice vibrates those silicon to oxygen bonds. And that's a characteristic broad sweeping curve that gets stronger at longer wavelengths. So basically what we're seeing here, this left side or right side of the curve is the left side of that LP01 mode cutoff peak, that's the bend edge, but also superimposed with the material's IR absorption edge. Similarly, on the left-hand side, we see the attenuation goes up when we get closer to the UV. And that's a similar effect where we see the material absorbing the light. Instead of vibrational energy, that's actually electrons being excited to higher order or higher energy levels, electronic absorption. And that's why we see on the UV side increased attenuation as well. One last thing to illustrate on this curve, we show down here, again, single mode operation out here. Doesn't guide light past, very far IR, and then few moded multimode operation on the left side of the curve. We're going to show this graph one more time, and what we're doing here is comparing that to multimode fiber. So this is another measurement we took here at Thorlabs, and this is actually a fiber we make in-house as well, a 200 micron core multimode fiber. As you can see, the multimode curve looks different than the single mode curve. Not as many peaks. Does have a few peaks for a completely different reason. These are absorption peaks. For instance, this is a little bit of water that absorbs here in the glass. But we still see that IR and UV edge from the material absorption, and we don't see these peaks as modes are cut off. And we also don't see this region of very, very low attenuation like we see on the single mode curve. So that's really illustrating the difference between that multimoded operation and a single mode operation. I'll show you these curves one more time, and what we're looking at on this slide, same curves, we've just changed the y-axis to a log scale. And that lets us really examine that low attenuation portion of the single mode fiber. So we measured 0.17 dBs per kilometer in this fiber, whereas the multimode fiber, as you can see, never gets close. And that's all due to the fiber being single mode in this wavelength range. Won't go into it in detail, but 0.17 dBs per meter, what does that mean in real life? That means if you were, let's say the water in the ocean had 0.17 dBs per kilometer of attenuation rather than the hundreds it does now. You could be at the deepest part of the ocean and you could look straight to the bottom and you could see the bottom clearly. That's how clear, quote unquote, the fiber is, or how low loss single mode fibers can be. And that is due to the very mature manufacturing processes for fiber, but also due to the single mode construction. Okay, so we're on to the second to last part of the talk. We're going to quickly go over just a little bit of details on how we design single mode fibers. When we design single mode fibers, again, we're looking at this simple step index profile. And the two variables that we have at our disposal are the diameter of the core, so the width of this high index region, and then also the fiber's NA, which is really the difference in the index between the core and the cladding. So we can make it a large difference relatively between the core and the cladding, or we can make this step shorter, have a lower NA. So what we're showing here is two different fibers. Again, some microscope images. As you can see, very different core size. Can't see it in the image, but they also have a different NA. The one on the left has a lower NA. Believe it or not, these fibers have the same cutoff wavelength, even though the core is radically different and the NA is different. So we've chosen those two parameters, different parameters, but that combination gives us the same cutoff wavelength, different other light guiding properties, but same cutoff wavelength. So two different ways to design a single mode fiber. As a quick review, like I said, NA is a product of the index difference between the core and the cladding. So higher NA means a larger acceptance cone of light, higher or smaller critical angle, steeper angle to the core cloud interface, and stronger light guiding capability overall. Single mode fibers are typically in the 0.1 range, so it's a pretty small NA. Once we have that NA and that core diameter, we can do a little math to figure out how the fiber will perform. The first thing that's usually calculated is what's called the V number. In multimode fibers, when you have thousands of modes, the V number, or V squared, is proportional to the number of modes. For single mode calculations, when V is less than 2.405, that means that the waveguide only supports single mode operation. As you can see, V is a function of core diameter and NA, and also wavelength. As the wavelength gets longer, the V number gets smaller. Eventually it goes below 2.405, and that's where we have single mode operation. Again, illustrating that effect where shorter wavelengths are multimode, longer wavelengths are single mode. So if we plug in 2.405 and rearrange the equation, we can actually calculate the cutoff wavelength. This is the theoretical cutoff wavelength. There are some real world effects that make the fiber behave a little bit different, and the cutoff occurs a little shorter, but this is the theoretical cutoff wavelength of the fiber. And we can also use the V number to calculate the mode field diameter using this equation down here, or approximate the mode field diameter. So bouncing back to our example fibers, the larger core fiber, standard telecom fiber, this is basically the SMF28 design, 8.2 micron core, 0.14 NA, and the cutoff wavelength, if you calculate it, ends up being about 1500 nanometers. The small core fiber, and this one specifically is for splicing to high NA waveguides, is what it's marketed for. 3.28 micron core, an NA of 0.35, so much higher NA, much smaller core. And look at this, you get the same cutoff wavelength. Big difference being the telecom fiber, the mode field diameter is pretty large, just over 9 microns, whereas for the small core fiber, the mode field diameter, still larger than the core, but much smaller. Each of these designs has benefits. The larger core fiber is, of course, it's a much larger mode field diameter, and that makes it much easier to couple light in. You need still pretty good, but not quite as crazy precise mechanical positioning and aligning for good coupling efficiency. So this fiber turns out to be much easier to work with. The high NA fiber with a small core, pretty hard to get the light in, but once it's in there, first thing is we actually have a larger single mode operating wavelength range. So between the cutoff wavelength and that bend edge, it's actually going to be extended for the larger NA fiber. It's also going to be less sensitive to bends. So again, that higher NA means better light guiding capability. So for both micro and macro bending, it's going to be less sensitive. That being said, this 0.14, 0.11, is a typical NA. That was chosen because that's about as low as you can go and still get acceptable bend performance. So that's one reason why we go with fibers like this, because a good compromise between larger mode field diameter, still relatively bend insensitive. As I alluded to, this is the last little portion of the talk, there are some real world factors that can make fibers deviate from these theoretical performance that we've discussed. The first is microbending, which is a pretty interesting effect to me. Basically what this means is even if you have a piece of fiber laying on the table in a straight line, it's not going to behave like the perfect waveguide that is, perfectly straight. The reason for that is there's always going to be some microscopic bends in the fiber, microscopic stresses that bend the core a little bit. And so what that means is the fiber acts as if it's bent. And that's kind of baked into the fiber, even if it's straight. And if you have it in a deployment condition where you are putting like force on the fiber, let's say external forces, you can actually create more microbending effects. So it's going to act like it's bent even more. So some of it's baked into the fiber and some of it is has to do with the deployment. And the big thing that this affects is that the cutoff wavelength, where the LP11 mode is no longer guided, occurs at a little bit shorter wavelength than what we'd predict from theory. You might have noticed that actually in this talk for SMF28, I calculated the cutoff wavelength as 1500 nanometers. On our measurements, we measured it at, I think it was around 1325. And one reason for that is microbending. In addition to the cutoff wavelength shifting to a little bit shorter wavelengths, the bend edge does as well. There are some things we do in fiber manufacturing to minimize this, and one notable example is we use what's marketing usually would call it, the fiber marketing materials would call it a dual acrylate coating. And what that means is we have our glass fiber, and this is a cross section again of an SMF28 fiber. So we have our glass fiber, and then we have a very soft, squishy inner coating. So squishy that when we cut the fiber, you can see we disturbed it some here. And that's really like a shock absorber to try to minimize microbending. And then we have a hard outer plastic coating that protects the fiber mechanically. One other real world effect I'll just go over real quick has to do with that index profile. So if we're designing a fiber, we can sketch out, whatever we want here. But in reality, it's pretty hard to achieve a perfect stepped index fiber. And that's really due to how we manufacture the preforms or the glass for fiber. Process called MCBD is used to deposit this glass in layers. So we usually see this sawtooth pattern here. And what that is that in each layer, we don't have a homogeneous index from the top to the bottom. Additionally, we usually see this dip in the middle of the core in index, and that's from the index modifying dopants we add to the core to raise the index. So we get some evaporation of those in some of the processes we use to make the glass in the center of the core. We also get a little bit of diffusion of those index modifiers between the core and the cladding when we heat this glass and draw it into fiber. So we don't have a perfect step function. It's a little bit of a gradient on the edges of the core. So you see, like I said, this is our actual measured real world index profile of a fiber, and not quite the same. Luckily though, the fiber does behave almost as if it has the ideal step index profile. Again, we're just scratching the surface on real world effects. We have a talk on the website about fiber manufacturing, which does go into this in more detail. And with that, the last thing to talk about is we do have part 2 of this webinar coming soon on November 3rd. We hope you can join us. That'll be, now that we have this theoretical understanding of how the light travels through the single mode fiber, that will be more focused on, in practice, how do we use single mode fibers, like coupling light into fibers, what's the best way to set that up? How do you actually align the system to get good coupling efficiency, and some other interesting topics. So we hope you'll join us for that. With that, thanks to everyone for listening today. I hope you found this webinar interesting.
Thanks, Dave. We've had a few questions come in that I'll read off to you now. I believe we have about 5 or 10 minutes.
Sounds good.
So first one, how does the mode field diameter compare to the physical core size?
Good question. So there's a couple things to think about there, and we did simplify a little in this discussion. So if I go back to this slide here, you can see core diameter 8.2 microns, mode field diameter 9.05 microns, and that's because that fundamental mode propagates in a region slightly larger than the core. How I simplified, though, is you'll notice this is specified at a certain wavelength, and that's because the mode field diameter is a function of wavelength. It gets larger. The core size, of course, stays the same, but as you increase wavelength, the mode field diameter does get larger. And that's really what we're seeing, is that mode grows as the wavelength of light grows, and that's why eventually it can't be guided by the core. So yeah, it's always going to be a bit bigger than the core, and it's also going to be a function of wavelength, and it's going to be larger at longer wavelengths.
Okay. Another question is more about fiber manufacturing. How are the layers created in a preform and then maintained during the draw process?
Sure. So shameless self-promotion, I'd refer to you first of all to the fiber manufacturing talk I gave a couple months ago on our website, where we talk about the MCVD process in detail. But in a nutshell, we make a tube, and we deposit glass on the inside of the tube in these different layers, and that uses chemical vapor deposition, where we deposit silica glass soot onto the inside of this tube, and for each layer we can define the index by adding index modifying dopants. Then we heat that silica soot and sinter it into glass. We also pull a vacuum on the inside of the tube, and it collapses into a solid preform. And then in the fiber draw process, we do heat the glass, but we're careful to not heat it too much, so we don't see too much diffusion of the index modifiers, so we keep the core clad structure relatively intact.
Okay. Actually, since you're on this slide, I'm not sure if you can see on that graph, but how sharp is the edge of the index step? Does it go from high to low in 1 nanometer, 100 nanometers?
It's a good question that I don't really have a good answer for. It's pretty hard to measure because we're getting into trying to measure something that's a lot smaller than the wavelength of light. So this index profile is taken with a method that's a little bit analogous to an A scan on an OCT. We're looking through the side of the fiber, and we're using a certain wavelength of light to probe the fiber. Shorter wavelength gives us better spatial resolution, but it only gets so good. You can look at a fiber on an SEM and look at the core clad index there. But yeah, you can see a gradient. I don't have a good answer quantitatively on how large that gradient's going to be.
Makes sense. This is a question more about usage. Could you use, so you showed two single mode fibers with similar properties but different physical attributes.
Mm-hmm.
Could you use a standard telecom fiber for easier coupling and then taper it down to a high NA fiber with similar guidance for better light guiding or better insensitivity?
Yeah, there are ways to do that. It gets a bit complicated, and that's one of the things that we'll talk about in part 2. But there are, in addition to, like you said, launching into this fiber and tapering down to this fiber, there are products marketed that have what we call a thermally expanded core on the fiber. And so the deal there is you would take a fiber like this and you would heat just the tip of the fiber, and you're purposely going to diffuse some of the index modifiers out into the cladding sum. So you basically make the fiber right at the tip, the core even larger. And that will let you couple the light into the fiber, even larger than this mode flow diameter here for easy coupling. So kind of the effect that I think the question is asking about is a thing that, yeah, we purposely do even to the telecom fibers. There's also fibers out there, again, keeping in mind that the index modifiers that create the core versus the cladding can be mobile. If you splice, let's say you splice this fiber to this fiber, there are certain fibers engineered so that in the smaller core fiber, the dopants, as it gets heated for that fusion splice, will move some and again create a natural taper on that splice, so you get good coupling efficiency. So yeah, there's definitely a lot of ways to do it, and that is something that it is engineered into certain fibers.
Gotcha. How can imperfections in the rotational symmetry of the fiber change its single mode operation? Is it similar to the effects of microbending?
Yeah, so we see basically a small defect is going to contribute to microbending. If you have a large defect, then scattering becomes an issue. If it's a defect, my cartoon here, I'm showing a defect in the cladding that perturbs that core cloud interface. Let's say you had a defect in the core, that's going to straight up block the light if it's of sufficient size. So yeah, all these things are going to affect the performance of the fiber, in a way that's not going to help the attenuation.
Yeah, I believe there'll be some polarization dependence too, right?
Yeah, good point. Good point.
Okay. Time for a few more. Is there an intensity threshold at which single mode fibers start acting like multimode fibers? That's the question.
Yeah, interesting question. So there's a few things that happen as you increase the intensity of the light in the fiber. And let me scroll back to where we show the fundamental mode. So you can't really muscle your way into fitting, quote unquote, more modes into the fiber. Really, it's a function of the wavelength of light. However, if you notice, the fundamental mode is most intense in the middle of the core. So that's where we start to think about things like nonlinear effects, where the intensity of the light can actually locally change the index of the core. So the index can be a function of the light intensity propagating through. And that can, for instance, all sorts of different things like supercontinuum generation springs to mind, where you purposely want nonlinear effects, or sometimes in telecom fibers, we purposely try to not have nonlinear effects. Things like spectral broadening and things like that. That's really the dominant thing that happens, though, as you really increase the optical power in the fiber. And then, of course, at some point, the light is too intense and you reach the damage threshold of the silica glass and burn the fiber. But that's really the things that happen as we increase the optical power, not so much changing the behavior of the modes propagating through the fiber.
Gotcha. Okay, so we have time for one more question. If you could go to slide 26.
Sure.
How did you take the photo on the bottom right?
I'm glad somebody noticed that photo. So this photo, we've shown it in a few different webinars because I think it's really cool. What we did is we cleaved. This is a multimode fiber, of course. We did a flat cleave on the end, and we have this fiber under a microscope immersed in index matching oil. So that's what lets us see the fiber without the curve on the front. And the index matching oil happens to scatter this blue light in the fiber. So this light is propagating through the fiber. You can't see it in the glass because it's not scattered by the glass. That's on purpose, the fiber design. Once it leaves the fiber, you can really visualize that cone of light exiting the fiber because it's scattering off of the oil that we have the fiber immersed in under our microscope.
Yeah, well, thanks for revealing your secrets. And with that, we're going to close it out. So just a reminder to everyone, part 2 is on November 3rd. That's a webinar on the practical usage of single mode fiber. Thanks to everyone for attending.